In this example, we're told we have an ordinary shower where hot water comes in at a certain temperature and it's mixed with some cold water at a different temperature, and that we want to have a steady stream of warm water leaving the shower. And in order to do this, we need to determine the ratio of the mass flow rates of the hot to cold water. We're told to assume that heat losses from the mixing chamber are negligible and that the mixing takes place at a pressure of 20 psia. So the picture here is some sort of mixing chamber. I'll just draw it like that. So this is our mixing chamber. And we have some water coming in here from the hot side and from the cold side, and then it's going out mixed like that. So this will be we're going to have a control volume here and do a control volume analysis using the first law in order to determine this. So the reason I'm thinking the first law is because we're looking at changes in temperature. So these changes in temperature are related to the internal energy or the specific enthalpy of the water. So let's go ahead and apply the first law here. We'll go ahead and expand it out, or write out the basic equation first. It's just a lot to write down, so you have to be patient. Okay, so we now have our first law written down. Let's go ahead and start to simplify it. So first of all, we're going to assume that we're dealing with a steady flow here. We're not told anything about time variation, that it's transient or anything like that. So we'll just assume we're dealing with a steady state situation. We're also told to assume that heat losses are negligible from the mixing chamber. So that means that there's no heat transfer. That means it's adiabatic. We also don't have any other kind of work terms. There's no propeller or electrical power or anything like that going into the mixing chamber. So the work term is going to be zero. It's what we call a passive device. Passive means that there are no active mixing elements, or no active elements in there, like I said, like with a electrical work or a spinning paddle or any moving piston or anything like that. So it's passive. So that just leaves the incoming enthalpy and the outgoing total enthalpy terms that we need to consider. So typically with a shower mixing chamber, you don't have large changes in elevation, so the potential energy terms would cancel out. There's just no large changes in elevation there. Similarly, there are no large changes in kinetic energy typically. So changes in kinetic energy and potential energy are negligible. They may in fact be there. They're not necessarily exactly equal to zero, but they're just not very large. Certainly not very large compared to the change in the specific enthalpy of the incoming and outgoing streams. Okay, so then that just leaves our incoming specific enthalpy terms and the outgoing specific enthalpy terms. So let's go ahead and expand that out. So coming in, we have the mass flow rate of the hot stream times the specific enthalpy of the hot stream, plus the mass flow rate of the cold stream times the specific enthalpy of the cold stream. So we're talking about these two terms here. Those are the inlet ones. And then we have the outlet, so it's the mass flow rate of the mixing stream, the mixed stream here, times the specific enthalpy of that mixed stream. And before I go much further, let me do another thing. So we have these three mass flow rates: the mass flow rate of the hot stream, the mass flow rate of the cold stream, and the mass flow rate of the mixed stream. But I know that if I apply conservation of mass to that same control volume, I can relate the mass flow rate of the mixed stream to these incoming streams. So let me do that. So let's apply conservation of mass to the same control volume. So we'll just write that one out. It's a little easier to write out. Again, we're dealing with a steady state, so that first term is zero. And so what we'll have is the mass flow rate coming in would be m dot hot plus m dot cold. And then going out, we'll have the mass flow rate of the mixed stream. And so it's 0 is equal to m dot h plus m dot c minus m dot m. So we can rearrange that to get the mass flow rate of the mixed stream. It's exactly as you might expect. The mass flow rate of the mixed stream, this is the stream going out, will just be equal to the sum of the mass flow rates coming in. So we can take that expression and substitute it in up there. So let's do that, and then we'll expand it out. Okay, and then we're trying to find the ratio, right? If you go back up to the problem statement, it says determine the ratio of the mass flow rates of the hot to cold water. So I interpret that as being, I want to find m dot h over m dot c. So the ratio of the mass flow rates of the hot to cold water. So that's what I'm interpreting that to be. So what I'll do down here is I'm just going to divide everything by m dot c, right? So this will be m dot h over m dot c. This one will just be hc because the m dot c cancels out. Here we have m dot h over m dot c plus 1 times hm. And then I'll go ahead and gather this term and this term together. And then I'll bring those over to, let me go ahead and bring these terms over to the left-hand side while I'm at it. So this will be m dot h over m dot c times hm minus hc. I'm just doing some algebra here, is equal to hc minus hm, and then I can solve for my ratio of mass flow rates. So this will be hc minus hm all over hm minus hh. Okay, so that's how I'm going to find my ratio of mass flow rates if I've done all my algebra correctly. So just to kind of recap for a moment here, we chose our mixing chamber as our control volume. We wrote out the first law because we were thinking that, we're looking at changes in temperature, so that's likely to be a first law analysis. So we wrote out our first law for that control volume, simplified it, assuming steady state, adiabatic, that the device is passive, meaning there's no spinning shafts or electrical work or anything like that. We said the changes in kinetic and potential energy through this mixing chamber are really negligible for a typical shower mixing chamber, so that just leaves the specific enthalpies. We simplify, so this is our simplified first law. We made use of conservation of mass that told us the mass flow rate going out is equal to the sum of the mass flow rates going in for steady state conditions, and then did some algebra to end up here. So now to find the ratio of mass flow rates, we just need to find the specific enthalpies of the different streams. So we can do that using thermodynamic property tables. And if you do that, we'll get the following. This is approximately true. I used a particular table for English units. I can't remember exactly where I got which table I used. It was out of a textbook. But I got something that looked like this for the cold stream, for the hot stream, get this value, and for the mixed stream comes out to be 78.02 BTUs per pound mass. And again, these values come from, they're actually they're compressed liquid approximations for the liquid water. So when you're taking a shower, it's not steam, right? It's just liquid water. So that's a compressed liquid. So we use the compressed liquid approximations to find the specific enthalpies. Remember, the specific enthalpy compressed liquid approximation looks like this. So the specific enthalpy for compressed liquid at some temperature and pressure is approximately equal to the specific enthalpy for the saturated liquid at the same temperature plus the pressure we're operating at minus the saturation pressure at the same temperature times the specific volume of the saturated liquid at that same temperature. So that's how these quantities here were found. We were given the temperatures in the problem statement, right? Up here, 140 degrees, 50 degrees, and 110 degrees. We were given the pressure of 20 psi. If I recall correctly, the pressure contribution term is very, very small. So the compressed liquid specific enthalpy is pretty close to the saturated liquid specific enthalpy. So I believe these numbers are really just coming down to this because these terms are very small. Anyway, if you plug those in, what we'll get is the mass flow rate ratio comes out to be equal to 2. Nice round number there. So if you want your shower to output nice 110 degree Fahrenheit water, if the incoming water, the hot water is 140 degrees Fahrenheit and incoming cold water is 50 degrees Fahrenheit, you want to have that hot to cold ratio equal to 2. By the way, just as a side note, 110 degrees Fahrenheit, that's a pretty warm shower, so that's pretty toasty, but it's okay. 50 degrees Fahrenheit for cold water, that's pretty typical for cold water coming into typical residential house. It might be a little warmer than that, but that's pretty close. 140 degrees coming out of a hot water heater is pretty hot. In fact, normally you wouldn't have your hot water that high. You could risk scalding yourself if you don't have any cold water to mix with it. So normally you wouldn't put your hot water quite so high. It'd be closer to maybe, 115 to 120 degrees Fahrenheit at most, typically. Otherwise you could risk scalding yourself. So there's my public service announcement to go along with this example. All right, we'll go ahead and end things there.